So good afternoon or good morning, everyone, and thank you very much for joining us today. So today we have the pleasure to welcome Dr. Sascha Brune, professor at the University of Potsdam, and also head of the Geodynamic Modelling Section at GFZ Potsdam. And he will discuss geodynamic modeling of rift and carbon dioxide degassing. So Sascha, the floor is yours.
Thanks a lot for the invitation, and thanks a lot for organizing the seminar. So I was asked to present something that is related to volcanoes, because the sessions this year are supposed to be related to that, and I have not much experience in volcanoes, but the closest that I could get is this CO2 degassing. That's why I will present first some basics on geodynamic modeling, what we do, what can be done, some basics on rifts, and the importance of rifts in the Earth system, and then I will switch to CO2 degassing study. And the entire story, in a way, is encapsulated in this image here from James Keenan from 2017, who draw a nice sketch based on a paper by Fisher and Foley, and Tobias Fischer is in the audience here, and a paper that I published in that year that links the deep lithosphere and the upper mantle and the processes there to CO2 degassing along rift faults, the history of the rift systems through time, and how that relates to the evolution of CO2 in the atmosphere and the evolution of the climate over the last 200 million years. And let's take that as a motivation for looking into rifts to link them to Earth system sciences and to the carbon cycle. So the talk that I will be giving has three parts. First, I want to focus a bit on the processes of rifts, the motivation, why we should study them, and which kind of methods I'm personally using to study them. Then I will focus on rifts and their interaction with plate motions, and then I come to the CO2 degassing in continental rifts. So first, some basics. Rifts are intrinsically transient plate boundary. It's a constructive plate boundary, but what I mean with intrinsically transient is that there's never a real steady state within a rift system. It's not like in a mid-ocean ridge where you can say this kind of structure, thermal structure, mechanical structure is the same for and remains the same for tens of millions of years, or the same in subduction zones where if the slab dip is not changing much, then the configuration stays the same for a very long time. In rifts, this does never really happen because they are the places where continental plates are breaking apart, and that's why the process of breaking defines a rift by itself. So it's never really in steady state, which makes it dynamically complex and dynamically also interesting. And of course, rifts can evolve into a future ocean when the lithosphere is broken apart, but they don't have to. And there's many examples where rifts never made it into an ocean, where they just remained as scars in the landscape of the continents and are still visible today. Rifts are places where we have a lot of interaction between forces, so we can have far-field forces that put the continent into a tensional stress regime. We can have mantle tractions. They can uplift the plate and generate gravitational potential energy that helps to extend the plate, or horizontal mantle tractions that just drag the plates along. And there's a lot of lithospheric scale buoyancy forces that arise from interface heterogeneities and buoyancy in general. And then there's a lot of processes that act as weakening mechanisms or as strengthening mechanisms during the evolution of the rifts. I will not go through all these details here, but we have written a nice review where you can read up more details on these things. When we go to the rifted margin stage, when the rift has been successful, the rifted margins can have classically been grouped into two kind of classifications: magma poor and magma rich. In magma poor settings, we will have faults that often dip towards the ocean. We may have exhumation of mantle. We have a little bit of sediments in these fault-bounded basins. and finally the continent-ocean transition. In magma-rich systems, we have, as the name says, a lot of magma. This can be visualized in geophysics as underplating. There can be volcanic extrusions. There can be these faults that dip towards the continent in magma-rich systems because they are loaded by all this magma and volcanic rocks that pour out at the rift center and that create these seaward dipping reflectors here. So these are classically geophysical seismic reflection surveys that have been interpreting these kind of structures, and they have been a type classification for magma-rich systems. And then there's also a lot of margins where they are not as clear-cut as being one or the other. In this image here, then they are classified as intermediate, and they are actually also really interesting because they give us some insight on the timing of the arrival of volcanism, which can relate to decompression melting due to thinning or to the arrival of a plume or to any process that affects melting. And if you're interested in these kind of rifted margin formation studies, then I recommend this review paper. Now, rifts are largely dominated by two main processes. One of them are faults, and faults can have many, many different scales. So that's I find really exciting topic about structural geology or plate tectonics in general, that we have these cross-scale processes. We can see faults that activate small-scale foliations, and the faults are rather small. Faults can coalesce and form really big border faults, like the ones here in the main Ethiopian rift, with offsets of several hundreds of meters in extreme cases. And finally, in rifted margins, I'm going back and forth between these two settings. We can see these large-scale faults that have a depth extent of several kilometers and that accommodate the extension during the early and the late stages of rifting. I mentioned two main processes that affect the evolution of rifts. So faulting and brittle deformation is one process, and the other process is volcanism, of course. And we have some really nice examples of big impressive volcanoes in East Africa or some lava lakes. But we can also study volcanoes in rift systems or at rifted margins through seismic reflection surveys. In this case here, offshore Australia, where some of the Syn-rift volcanic edifices can be imaged in 3D seismic cubes, and one can learn a lot about the interior of the structure of these volcanics by cross-cutting through them and interpreting the structures that you find in them. And because it's often easier to have big seismic surveys on water, because you can do it with ships, you don't have to carry your seismometers around. Many of these insights on the interior structures of these volcanoes can be derived from these offshore experiments in rifted margins. Why are rifts interesting beyond the fundamental aspects? There are also sites of large georesource formation, and one of them is sediment-hosted ore deposits. These are zinc, lead, silver, and others that are also called clastic-dominated deposits, which means clastic. These are the sediments that fill the basin. Faults generate accommodation space. Sediments fill the basin, and these are derived from often from sites next to the rift, and they are transported over relatively small distances and are relatively coarse. That's why these are these clastic-dominated deposits. And another feature to form these deposits is hydrothermal flow, that water can flow along these faults that are omnipresent in rift systems, and by that concentrate ores by leaching minerals from deep layers and then precipitate them in shallower layers where the geochemical conditions and the temperatures are right. And one can abstract these kind of recipes for sediment-hosted ore deposits by having a certain set of layering and a certain set of fluid flow. And with that abstraction, one can actually model this process, which we did in that study here by Annick Lerum as first author that was just published a few months ago, where we answered or addressed the question, which kind of tectonic settings are particularly favorable for generating these conditions and to generate large-scale CD-type, plastic-dominated type ore deposits. And we found that narrow asymmetric rifts are particularly prone to do that because they have a long-lived history of faults, and they have very deep basins that provide the hot temperatures that we need to leach the minerals from this clastic sediments. And we find a mineralization window of 1 to 3 million years, which can help to identify potential regions in the long run to find maybe new deposits. Yeah? We have to understand the process in order to make testable predictions. Another motivation to study rifts is then, of course, CO2 degassing. I took some numbers here to show you how much potential rifts have. So fossil fuels, this is the number of how much gigatons carbon they contain. And mankind has been burning these reservoirs, which led to the prominent increase in temperatures that we experience today. So these fossil fuels have 10 to the 3 gigatons gigatons of carbon. But they are only a really small portion, and the deep rocks of the lithosphere, of the upper mantle and of the lower mantle, they contain 1 million times more carbon than the fossil fuels. And studying pathways, how these deep rocks and the deep carbon can be released towards the surface, that was one of the motivations for the study that I'm going to present later on. There are many more rifts than the East African rift. It's a prominent one. It's the largest one today, and it's extremely exciting. But rift research should not focus only on one region, but try to integrate what we know from all the other regions as well. And in this compilation from 2001, Schenker and Natalin compiled everything that was known at that time about rifts. They put them on the map, and you see that literally the world is scattered with rifts. We have failed rifts like the West African rift here. We have some failed rifts in North America where the Great Lakes are. We have some failed rifts here in the North Sea. And then we have many active rifts, many successful rifts that form the oceans of the Atlantic and of the Indian Ocean. One way to study rifts is geodynamic modeling. That's what I'm doing and what my group is doing. And modeling always comes with simplifications. So I found this nice picture here in Iris van Zelst's Geodynamics 101 study, where they compare nature and the models and the different hierarchies of simplifications. So one can set up models that are complex, one can set up models that are simple, and all of that is allowed as long as the question that one wants to address can be addressed with sufficient detail to justify these models. So only because models are simple doesn't mean that you cannot deduce interesting results from them. You just have to adopt the questions accordingly. And of course, you have to be careful that you do not oversimplify. I want to stress that numerical models are not the only kind of modeling for geodynamic questions. There are plate tectonic models, which I will show later on. Then there are numerical forward models, which I will introduce in a moment. There's, of course, analog models, which are much, much older than numerical models and yielded profound insights in the structural evolution of fault networks, for instance. And there's analytical modeling techniques where you just write up equations and where you are more on the simple side of the things, but where you at least, instead have really transparency of the solution. If it's mathematically, analytically shown, and if your assumptions are correct, then it is really prone to yield extremely robust results. For the numerical modeling studies, we generally solve 3 equations if we want to investigate long-term evolution. That's the equations of mass, momentum, and energy. I won't go into the details, but you can read up the details in this paper again. So we use physical first-order principles to constrain our models, and we use data from rheological experiments that give us the parameters for the viscous, elastic, and the plastic bits to make sure that the models that we run are actually constrained by data. Of course, we also add a lot of other data points, buoyancy, we need the density, We need the boundary conditions. How fast do we pull the model? So modeling scripts that we run are usually really, really long and contain a lot of input data. And if we do that, then we can reproduce main structures. And I want to show you one of those models. So this is a thermomechanical model that is a geodynamic model that's called aspect that we have linked to a surface process model called FastScape. We impose velocity boundary conditions, which means we pull at the sides. We push in material from the bottom, and otherwise we don't do anything to the model. We don't impose faults in the middle. We don't steer how it is going. It is all self-consistently evolving. So it's in a way more like an experiment than a model that is trying to fit something. So it's this is like the philosophy of these forward models. All of these codes are open source. They can be downloaded from the internet, and the communities of these two codes are very welcoming. So if you are interested, I recommend that you try this out. So if I run the model, then we see that we get a set of faults. These faults coalesce. We get some big border faults that are eroding over time. You might not see it as fluently as the model actually is, but I'm just stopping it now. I know that when I'm looking at animations like this from the other side of the Zoom screen, then they are super jerky all the time. So let's just stop here and explain this a little bit. So we have the uplift of the rift shoulders from our border faults. These shoulders are eroding, and the sediments that are generated are deposited in these basins here. So these are the fault-bounded basins that I mentioned earlier on. During this particular model, we have first a very symmetric setup with these two border faults, and the symmetry is now broken at a given stage, about this time here, and we generate some asymmetry. And this asymmetry leads to the rift center migrating from where it was in the middle between the two border faults to the left. This process of rift migration leads to the transfer of blocks from one side to the other side. So these crustal blocks here from the upper crust, they were originally from that margin, and they are now actively transported across the margin all the time. The same is true for these sediments from this infill that is dumped into the fault-bounded basins by rivers that are coming from the rift shoulders. And so we have a very complex evolution of these tectonic sedimentary systems here. We have interesting ups and downs that relate to flow of the asthenosphere and to the degree of how much we can sediment, so we can generate unconformities, age gaps, erosional unconformities, but also syn-rift, so post-tectonic unconformities that have been classically interpreted as breakup unconformities, but they are not formed in one time step, not during breakup, but rather as a diachronous feature where that track the migration of tectonic activity. Eventually, this process of rift migration stops. We localize in the as a symmetric system again, and this is when we would infer that this is continental breakup is happening. So in this kind of model, we don't have magmatic additions. People around the world are working on adding dikes and magmatism and underplating to these kind of models, but we are not quite there yet. So we don't generate oceanic crust, and we cannot really define the moment of when the stable ocean spreading initiates. So for these kind of models, we often stop at that part and don't interpret the oceanic domain, but rather the structures that we see at the rifted margin. So on this side. And if we zoom into that side, that is now the same model in a different representation. We can compare these kind of model interpretations and the model evolution to seismic surveys from rifted margins, in this case from the Norwegian margin, where we can find similar structures here. And this is what is the biggest gain of these models, comparing to structures and understanding under which environments and why these structures have formed. So we see the syn-rift sediments here colored in green, post-tectonic sediments that form these sag basins with an interface between them. We see these ocean wall dipping normal faults, so all structures that we see in the numerical model as well. And once we know how to relate the model to the structures, then we can go back to the models and infer pressure, temperature conditions, and favorable conditions for geo-resource formation. And this is what I showed you in a few slides earlier. So to conclude the motivational wrap-up part, I want to highlight that the last year has seen, or the last 2 years have seen publications of several review papers on rifts and rifted margins. And if you're interested in these kind of topics, then I invite you to take a look at them. So coming to the second part, rifts and plate motions. What we are often seeing are maps of plate motions for rift systems. And that's true for the East African rift and for the Aegean rift here. And these plate motions we often take as given. They are constant over observational timescales. They don't change by large degrees unless we have a big earthquake. But plate motions generally are not changing for our timescales, for decadal timescales. And so it's interesting to ask the question whether the rifts have actually an impact on these plate motions or whether they are just passive receivers of these plate motions. And that's what I want to address in this part of the talk. For that, we have to go back to the really classical explanations for why do plates actually move. So we look at the plate driving forces, and these are primarily slab pull, ridge push, and basal drag. And these forces drive the plates as they move around on the globe. And this is a plate reconstruction that shows the breakup of Pangaea with all the big rift systems that are dissecting the North Atlantic, the South Atlantic, the Indian Ocean, and eventually also East Africa. This reconstruction is done with visualized with the plate reconstruction software G-Plates that is also open source and that you can just download that from the internet and investigate which kind of motions did you see at a given time for that particular plate reconstruction model. But there's also a Python-based interface to G-Plates. And when I was a visiting researcher at the University of Sydney, I developed scripts that harvest plate tectonic information from G-Plates through a Python interface. And the images that I'm showing you now illustrate this approach. So if we take these reconstructions, we can put the coastlines on there and the continent-ocean boundary. And if we then close the oceans again, we will see that the continent-ocean boundary, so that's the part where we go from stretched continental crust to actual ocean seafloor, that they overlap. And that's because these kind of plate reconstructions are rigid. So you do not deform at plate boundaries. And that means when you reconstruct continents to where they fit, you have an overlap of the COBs because the deformation is not accounted for. And we use that to quantify when and where rifting was happening and also the kinematics of these rifts. So by having this overlap here, this light gray zone, we can define where rifts are. And from the PyG-Plates interface, we can deduce how fast did the rifts evolve. And that's what I'm showing here for the case of the South Atlantic opening. These velocities here, these colors, they show how fast the rift is evolving. And the size of the little circles here, the thickness of these lines codes for the same quantity. So if we step through the South Atlantic opening, we see that rifting started in the south, it propagated towards the north. So South America was rotating out of Africa here. And we see that the velocities are a bit higher in the south than they are in the north. And what we also see is that at about 135, 130, 125 million years, these velocities are accelerating dramatically. They go from the lower end of this range to the higher end. And that happens everywhere across the entire plate. So this can be visualized in that diagram that I'm showing here. We have the time evolution of from the onset of the rift to the final breakup on the x-axis. And we have the velocity of each small segment. I divided the plate boundary into small segments, and we measure the velocity at each of these segments. So the colors show you how long are the segments that evolve at that given velocity. And then the black line is the average across the entire active rift system. And what I showed you on the map is now visible in this kind of graph as well. We have a first phase of rifting where velocities are below or around 10 millimeters per year. Just to remind you, the East African rift is extending at 5 or 1 or 2, with a maximum of about 5 millimeters per year. So that's the typical rate for big rifts to start with. The South Atlantic did the same. And then we had this acceleration phase between 130 and 120 million years approximately. We went to 40, 50 millimeters per year. And just to illustrate that this is not a singular feature for the South Atlantic, the same is true for the North Atlantic, for America, Iberia, Australia, and Antarctica, for essentially all big rift systems that dissected and led to the fragmentation of Pangaea. Just to hammer the message home, it's the entire continent that has been speeding up as the rift was evolving through time. So entire South America going faster, entire Australia going faster away from Antarctica, entire North America moving faster away from the rest of Pangaea. So, of course, we have to ask the question, why do we have these plate accelerations prior to breakup, and why are they so rapid? And before I show you a numerical model that reproduces these features, I want to make you think a bit about the velocity of plate boundaries in general. So rifts are generally slow. East Africa with about 5 millimeters per year in the north, and really millimeter or below detection limit in the south, while the mid-ocean ridges are an order of magnitude faster. Even the relatively slowly spreading mid-Atlantic ridge has 2.3 centimeters and 3.5 centimeters. So it's just measured even in a different unit. And then the East Pacific rise with 16 centimeters is even in an order of magnitude faster. So when we transition from a rift to a ridge, we kind of should expect this kind of speed up. So let's look at this transition now with numerical models. This is a similar model as I showed you before. It's in a way a predecessor of the models that I showed you from a bit earlier stage, but the setup is the same. We pull with the velocity at the sides, we put material back in from the bottom, and that is the same classical velocity-driven setup. But to answer the question on how do velocities evolve, we cannot put velocities in. That would just be not fitting the bill here. So we instead put forces in. We say we have a given plate driving force that is entering into our model through the plates, through the left and the right sides, and then we get velocities as an output. And that's what I'm showing you here. So this is our model setup with upper crust, lower crust mantle lithosphere, and the visualized the background field that shows the second invariant of stress. So it shows us how much strength does the plate boundary have. So essentially the yield strength profile here on the right is imprinted on these stress distributions, these vertical stress distributions. And if I continue through time, then nothing much is happening. We're at about 10 million years and nothing much happened because I pulled at a force that is similar to the strength of the lithosphere. These little dots here, they will become velocities in a moment, velocity arrows. And that happens when the lithosphere thins through time and it's weakening through time. You see now that the brittle layers of the upper crust and the lower crust, they are starting to connect, they are thinning. There's hotter astronosphere upwelling here. And in the moment when these big faults form and when we neck the lithosphere efficiently, the velocities at the sides are going up because this weakening here has to be balanced with the plate driving forces. And the only way to do that is by increasing the velocities. And once we start localizing, we have a runaway feedback. Faults are more efficient, faults are weakening, lithosphere is necking, hot material comes in. And so we go from a strong state to a weak state, and that leads to this increase in plate velocities. And then we end up with breakup. So to plot that in a similar graph as I showed you with the plate reconstructions before, we have full extension velocity on the y-axis and we have time on the x-axis. And we have a phase that is slowly extending, but not much seems to be happening in terms of acceleration. And then there's a phase of relatively rapid acceleration when all these feedback mechanisms between strain softening and lithospheric thinning kick. And then these velocities would actually go out of the roof if I wouldn't cap them here. And I say at this time, this is when the breakup happens. This is when the mid-ocean ridge that we formed, or the rift that we formed, is so weak that it does not have a say anymore on the plate velocities. Now the velocities are controlled by all the other plate driving forces, basal drag and so on. So we ran these models with very different settings. The blue line was the reference model. Then we have a weaker crust. We have a thicker crust. We have a colder lithosphere. But the duration of the speed up changes a little bit, but the main message still stays the same. So why do we have these plate accelerations? Why are they so rapid? It's because rifts is where plates play a tug of war, where plates are diverging. And if you say that the forces of these little boys here is constant, and we have a strain weakening rope in the middle, then this will lead to rupture within a relatively short time frame. Everybody will fall to the ground. And the process behind that is that we have this weakening process in the middle. So if the rift strength goes down, the velocities go up. And if the velocities go up, then the rift strength goes down. And the simple explanation for that is when something breaks, things accelerate. So that means when we think of what drives plate motions, of course, the main driving forces, slap pull, ridge push, basal drag, they are acting all the time. But there are times in Earth's history where rift strength loss has a big say and where this process controls the velocity of the plates involved during rifting. Now, this has also interesting implications for rifted margin structures, because it means that if the near shore domains, the proximal margin here, if that is formed during the early stage of rifting, then this one would experience the much slower extension. And the distal margin, further outboard, it will have experienced much faster extension. And since extension rate correlates with upwelling, it correlates with decompression melting, it is somehow a natural thing to expect more volcanic products in the distal margin than in the proximal margin. Of course, this is a 2D approximation, and in reality, margins are much more complex, particularly along strike, and the speed up does not always affect the distal margin more than the proximal margin. But as an explanation for these kind of intermediate rifted margins, the plate acceleration can be really useful. So to conclude the second part, continent breakup generates plate accelerations. So rifts have a feedback on large-scale global plate motions because the rift strength loss is what controls how fast plates can move. So that process is key during that time frame. And we see that in quantitative analysis by numerical models with force boundary conditions. This can also be computed with analytical solutions, but in the interest of time, I will not show that. And we also have run numerical models in spherical coordinates where we do not impose the forces on the left and right side, but where they are generated self-consistently by mantle convection and plate tectonics, and we see the same process. So that brings me to the third part, the CO2 degassing part. Here I have to switch gears a little bit and talk to you first of all about the carbon cycle. What is it actually? And when people mention the carbon cycle, they generally mean the shallow carbon cycle. So that is this interaction, the strong link between the atmosphere, the ocean, between the biosphere, the human emissions, the soil, the fossil carbon. And then there's often a little volcano in the corner where these kind of images show the deep earth component. And that component is important for the long-term carbon cycle because all of these interactions take place on on their relevant timescales, but they are all smaller compared to the long-term evolution of the plate system of the deep Earth. Now, to motivate this study, again, I have this distribution of carbon in the Earth. So similar to what the numbers that I showed you before, we have fossil fuels where we have 0.005% of all the carbon on the Earth. And then the atmosphere is also a really small contribution, but that's what drives these climate changes. The mantle, because it's so big, concentration is much smaller, but because it's so big, it has 8 to 9%, and the largest concentration is actually in the core. So this is just to show you that any process that links the mantle, that can tap this mantle reservoir of carbon and link it to the atmosphere, can be really relevant for understanding how the deep Earth and the atmosphere are interacting. So how is carbon released from solid Earth to the atmosphere? Traditionally and understandably, the first place that people went to measure CO2 are volcanoes. So here the magma transports carbon to the surface. We generate gas by dissolving the gas from the magma. You get these bubbles, you get degassing along volcanoes. And this kind of degassing is happening not only during eruptions, but also during just the dynamics of the magma chamber. So you have a lot of CO2 degassing from volcanoes along cracks around the volcano. And so faults and fractures are also important features for CO2 release. Now, the difference between faults and fractures is that faults and volcanoes is that volcanoes are punctual, while faults cover the entire rift. So even though the concentration, so the flux density of CO2 release at volcanoes might be higher than along faults, the sheer large area that are covered by faults makes them also a potential large source. And there's another argument why faults are important for CO2 release, because volatiles and faults, they like each other. This is an image from James Muirhead, who gave the talk in the seminar a month ago, and who explains really well how the interaction between fault strength and the amount of volatiles and fluids that you have circulating along the faults is helping each other, because the fluids along the faults are reducing the effective friction coefficient. The water and the fluids, they just take up some part of the strength, and that reduces the effective friction. So fluid flow along faults makes it easier to deform along these faults. And there are several studies that measured CO2 flux in specific areas, but there's only a few studies that dared to extrapolate. And the reason is that its extrapolation comes with large uncertainties. I'm just listing a few studies that did that. So Lee et al. 2016, they extrapolated from the measurements that they did to the entire Magadi Natron area and found that that basin is releasing 4 megatons per year. And the basin is 9.2 thousand square kilometers big. Then we have Weinlich et al., who interpolated spring-based CO2 measurements over the Eger Rift in the Czech Republic and got this flux of 0.16 megatons per year. Central Italy, where we have a lot of carbonates in the ground, has a high flux of 3.8 megatons per year over that area. And the Taupo rift in the volcanic rift in northern New Zealand releases 0.45 megatons per year. So you see that these values, they are quite widely spread. And if you divide this total flux by the area, you find quite different values. But it means that rifts can have quite a large contribution to the atmosphere of CO2 over geological timescales. Now, let me bring you this argument again through that study here. I mentioned that before, Lee et al. 2016. What they did is they went to this Magadi Natron Basin and they measured several transects and used these CO2 gas accumulation chambers. So you have to carry them around, you put them on the ground, you wait until the chamber is filled with gas, and then you can measure a CO2 flux for an area that has the size of a vinyl LP. And if you do that, you can see high CO2 flux along your transect, and you find high fluxes, particularly where you have faults. So that explains this, or that supports this this point that I made before, that faults and fluids and CO2 release, they just like each other. You have higher fluxes along faults. And what they then did is they said, this is the area of the entire Magadi-Natron basin. We are extrapolating along all the faults that we have in these basins, and then we find 4 megatons per year for that basin. And then they also bring the argument that if you extrapolate even further, it means that 1,000 kilometers of rift will release 20 megatons per year of CO2. So the entire East African rift will release about 70 megatons of CO2 per year. And if you compare that to the CO2 that is coming out of mid-ocean ridges, you find, well, that's pretty much the same order of magnitude. So rifts are an important agent in CO2 released from depth. This kind of extrapolation, of course, comes with a lot of uncertainties, and it has to be taken with 1 or 2 or 3 grains of salt. And no surprise that these kind of inferences have been discussed in the community. And a year later, Hunt et al., they suggested that if you use another extrapolation technique, and if you integrate new data that they collected in the main Ethiopian rift, then the whole flux of the Eastern rift is actually 3.9 to 3.2 megatons per year. So instead of this large range with these large fluxes, they rather say it's rather smaller. But nevertheless, whether you have an order of magnitude more or less in degassing, there's still a lot of CO2 released from rifts. And in order to find out how much is actually coming out, we have to improve our observation techniques, essentially. So what I will do in the next final 10 minutes of this talk is I will address the question, how did rift length evolve through time? So no matter which kind of extrapolation you use, we find that more rifts will release more CO2. So I'm asking the questions, how long were the rift systems through time? And also, how does this compare to paleoatmospheric CO2? For that, I use again plate tectonic reconstructions similar to the ones in the talk before. These reconstructions are based on a lot of geophysical and satellite-based data. And I showed you this image before, so that's the same approach that I used before. I put Pangea back together. I analyze how, when and how these rifts occurred. And for this study, I also added those rifts that are not part of this plate tectonic reconstruction. As I showed you in the map before, Stenger and Natalin showed this really nicely, that there are many rifts that are failed, but they were still active at the time back in the days. So I add these red circles for those rifts that are not part of the full plate tectonic reconstruction. Now I play the animation in a way of the last 200 million years of Pangea breakup, and the more red you see, the more rifts we have and the more CO2 release we would expect. So we have first the opening of the North Atlantic, then the split between East and West Gondwana, then the split between India and Antarctica and Australia, the big cross here from a separation of South America and Africa, and the rifts in the interior of Africa. And we have a low in the late Cretaceous and early Cenozoic times. And then we have the North Atlantic separating, and then we get more rifts in Western North America and Southeast Asia, and finally in East Africa and then in the Mediterranean. So if I plot how much rift length do I have through time from this animation, then I get these two lines. The red line is showing just what I showed you before. The blue line is a bit more conservative if you don't believe in plate tectonic reconstruction. So the blue line shows only this Stenger and Natalin database. But no matter which kind of preference you have, we see a Mesozoic rift pulse from the early separation of Pangea, and we see a Cenozoic rift pulse from all the rifts that have formed during the last 20, 30 million years, including the East African rift. Now, this can be compared to the atmospheric CO2 content. All these little red dots, little gray dots, they show one measurement of a CO2, paleoatmospheric CO2 measurement. There are several kinds of proxy data that one can use to get these measurements. I won't go into details, but you see there's a certain spread. So that shows you how much we know about paleoatmospheric CO2. The gray band in here shows the mean proxy data plus minus 2 sigma. So that gives you a trend of how the CO2 evolution of the atmosphere is evolving over the last 200 million years. And we see a Mesozoic CO2 high, and then we see Cenozoic CO2 high. And okay, qualitatively, really qualitatively, we can relate these two to each other. To put this a bit on a more solid basis, I have been running these GeoCarb-Solve carbon cycle models. And as an input, I used these lines from the top. And so these are the lines that I get from these carbon cycle models that account also for the shallow carbon cycle and for the interaction of the biosphere with the geosphere. And still we see a similar trend. We have this Cenozoic high and the Mesozoic high that correlates with rift length. So that result is, of course, submitted to a lot of assumptions, and it's debatable whether that is really the case. And you could say there's all these subduction zones and arcs and mid-ocean ridge volcanoes that also play a role. So I use the next few minutes to show the caveats to this approach. So first of all, it's important to say rift length is not the only thing that controls what's going on. Maybe one should rather look at how much magmatic products do we actually generate. It's not so easy to infer that, but that would be a new research direction that would be interesting. It would be also interesting to go towards earlier times, so not only stop at 200 million years, but go deeper back in time. It would be interesting to have the carbon cycle more in a better representation than just in this very simplified GeoCarb-Solve carbon model to account for other gains and sources over the last that are better known over the last decades. And that image shows us how much CO2 can be contributed by rifts and arc volcanoes and mid-ocean ridges. So these are all important players in the global carbon cycle, of course. Another point is that, so going beyond rift length, it's also important to think of where do we have which tectonic units, because old continental lithosphere, like cratons, had a lot of time to get infiltrated by partial melts and to accumulate carbon at its base. So in this review paper here by Foley and Fisher, they estimated how much carbon can actually be stored in the deep root of the craton. And that root will then break apart, and when rifts dissect parts of the craton, it will be released close to the surface. So that means that the proximity of a rift to a craton will also have a big impact on how much CO2 we are actually releasing. And these studies have been integrated into that paper here by James Muirhead again, where they argue that the high CO2 flux in the Magadi-Natron Basin is related to carbon that is released from the deep root of the neighboring Tanzania craton. So in order to account for deep time CO2 degassing from rifts, we also need to account for the maturity of rifts, the distance to a craton, and parameterize that factor also into our models. Now we have started to do that actually. So I got funding for a big project here where we combine new kind of measurement techniques, where we explore drone-based CO2 flux measurements. We integrate geodynamic models, and we integrate long-term carbon cycle models. The project has started essentially earlier this year, so I can't show you results yet, but we are hoping to get some nice results over the next years. Before I finish the talk, and I have a look at the time, yeah, I think I still have 1 or 2 minutes, I would like to highlight another online seminar. So that's the Rift and Rifted Margin seminar that we have been doing with many great colleagues since Corona times, 2020. And we have this homepage, for those of you that don't know it, there's a YouTube channel from the seminar where we have recorded all the talks. And there are 3 talks here that I want to highlight particularly because they relate to the CO2 degassing story. So you're welcome to go on the homepage and to take a look. If you are interested in joining the session live, then we have a session every first Monday of the month. And in 1.5 weeks, we have a session on magma tectonic interaction, which also fits really well to the topic here. So you are welcome to join. If you want to join, then just set your name on this mailing list, and then you will get the Zoom invite through this mailing list. And I can also put that into the chat so that you can actually click on it. Oh, no, I don't have it right now. Well, I can do that later, maybe. So to summarize, numerical rifts models have a broad range of applications, from georesources to Earth system science. And I hope I convinced you that running these kind of models and comparing them to observations can lead to new insights in how structures form and how maybe also ore deposits form. Rifts are not just a passive player in the global scheme of plate tectonics, but they can actually control plate accelerations during the time of strong weakening, during the necking of the lithosphere. And rift-related CO2 release might affect the global paleo CO2 history, but we need a lot of more observations and integrated modeling data to ensure that results are embedded in the larger Earth system sciences. With that, I thank you for your attention. I'm happy to answer any questions you might have.
Thank you very much, Sascha, for your presentation, very clear presentation. Thank you very much. Anyone having question? You can either unmute yourself and ask directly Sascha, or you can write it on the chat and I will read it with my French accent.
Okay, well, I will start then. Sascha, that was great. Really, thank you so much for making the modeling very accessible and very clear. Very, very interesting. You briefly mentioned that you guys will combine melting models in the rifting model. And I assume that you will also combine that with CO2 and other volatile degassing, especially maybe water, sulfur. Just wonder how far away are you from that, and what melt models are you going to incorporate into those tectonic models?
Yeah, so the postdoc of that project has started in August, so you can imagine how much progress we could have made. So what we did, we based our workflow on the studies of Tobias Keller and Richard Katz. They have a 4-component melting model that we will integrate with our two-phase flow models. And then we can track how the carbon-rich component can be leached or can be freed from the deep lithosphere and be transported upwards through two-phase flow towards the lower parts of the crust. We will not integrate two-phase flow with the brittle deformation, because that, as we say from the same group and other groups, that leads to a lot of numerical problems, and also to the fact that we need really small time steps to actually resolve that process. And that is prohibitive if you want to run models over geological timescales. So we will have to find a parameterized version to bring the carbon from the base of the crust or from the base of the brittle part of the lithosphere to the surface. And we have some ideas about that, but it's a bit too early to discuss those.
Any other question? Okay, so maybe I'll go for one. I was wondering, what do we know the impact of the lips?
On CO2, yeah. So we can plot the impact of lips. Let me just see whether I have an image on those. I think this one will work. Exactly. So that image at the top, that shows you how much large igneous province area was generated. That's from a compilation of Richard Ernst. So it's not so easy to transform that into mathematic volumes, but it's just the area that is covered by the large igneous province. And so we have, this is the big breakup of the North Atlantic. Then we have, this must be Tristan and several other plumes that generated large igneous provinces. And then we have a far over here. And so if you try to correlate this with CO2, atmospheric CO2 reconstructions, you don't see a big correlation of that. And that can probably be explained with the fact that lips are formed during really short time frames. It's often less than 1 million year. The length is often not easy to say because of the dating techniques. Maybe it's also 500,000 year, but they are short. And that means that they are not generating CO2 over large time scales, but they are rather submitted to small, shorter metabolization of the CO2. So the shallow carbon cycle is really efficient in bringing down CO2 again. If you have higher CO2 in the atmosphere and higher temperatures, then the weathering rates are going up, and you get a lot of material to weather because of all the basalts after a large igneous province eruption. So there's papers that show that within less than 1 million year, the CO2 in the atmosphere goes actually back to the background state after a large igneous province eruption. So they can have punctual impact, and they can be disastrous for mass extinctions and for releasing a lot of volatiles into the atmosphere. But on the 5 to 10 million year time scale, they don't play a big role that is as big as the CO2 that comes from plate boundaries.
Okay. Yeah, I see. Yeah. We have a question in the chat by Clara Kimani. What is the flux of CO2 on the western branch of EARS? I see it talked about the Magadi-Natron Basin, only that is the eastern branch. What about the contribution from the western branch?
Yeah, that is a good question. So there have been a few studies that I'm aware of that looked at the western branch. I don't recall exactly the values that they find. No one dared to do any larger scale interpolation, but in the end, that means we don't really know how much is coming out. And the big difference between the eastern and the western branch is that we have a lot of magmatic products in the east and not so much volcanism in the west. So my first guess would be that you have less release because the magmas are what's transporting the carbon from depth to the surface. But there are some big volcanic provinces, Wongbei volcanic province, and then others further north where you can actually get high CO2 fluxes, but I don't know the exact values.
And if it comes from faulting, if the release use a pathway of faulting, yeah, you may not automatically. It may not automatically be smaller.
Yeah, well, I mean, they come through the faults, but they originate from magmatic bodies in the crust. And so if you have more magmatic bodies in the crust, then you probably also have more volcanic products at the surface. So like intrusions and surface release, they are often linked to each other.
Yeah. Okay, we have a comment from Reha Chandresh. It was a great talk, Sascha. Thank you.
You're
What
welcome.
a question. So anyone for a question?
Yeah, I just wanted to follow up on the LIP discussion, brief discussion. There was a recent paper that just came out where they, I think it was Ben Black was the first author, talked about passive degassing prior to LIP eruption, and that might also play a role in increasing the CO2 content in the atmosphere. The effect, I don't think was, I have to look at the paper again, but the effect wasn't very, very big. So it agrees with what you said, Sascha, that these are relatively short-lived events, even when you take into account, millions of years of passive degassing prior to eruption.
Yeah, thanks. I just looked it up, Black and Ayupa in Volcanica. Thanks for the tip.
I don't think it was Ayupa. I think it is Ben Black, Thompson Mathers on there, Leif Karlstrom. It just came out like a couple of weeks ago.
Okay, right. I look it up. They have been productive, it seems.
Yes.
Thank you, Tobias. Thank you. Okay, so maybe we'll close the session here. I would like to thank Sascha again a lot for his presentation and his time. Thank you very much. And also thank you very much, everyone, for joining us today. Thank you.
Thanks for organizing, Catherine.